Hello, you're welcome back to the third phase of the AI in Civil Engineering course. As you know, the first phase, the second phase, and the third phase are dedicated to data engineering. So all we've been doing so far is about data engineering. We've not started building the actual model, but this is the last phase of that. In the first phase, we did the data cleaning. The second phase, we did exploratory data analysis. And in this phase, we will be working on feature engineering. This will be quite faster than what we've done because whatever we're doing here is more or less what we've done in the past. So we simply just be copying the code, right? What exactly is feature engineering? Well, feature engineering simply means that we are applying some domain-specific knowledge in creating a feature that we do not have, but we need that feature. So we are going to create that feature from the available data that we have. So to make this simple, in our feature, let me say df.head, so I can simply just display our data frame. This is what our data frame looks like, okay? In our data frame, we have 8 features and 1 target. All of these features, they are independent in reality, but as far as concrete mix or mix design is concerned, cement and water are not entirely separate, okay? Because say, for example, you want to have a mix ratio of 1:2:4, which means 1 volume of one fraction of cement, then 2 fraction of fine aggregate, then 4 fraction of coarse aggregate. When you do that, you are not simply going to just add water into that mix. You will specifically pick a particular water to cement ratio of, let's say, 0.25. And then based on that ratio, you are going to calculate the fraction of water you will add in your cement and you add in your concrete, okay? So water and cement, they are not so independent, okay? So with that being said, I think water to cement ratio is more important to have as an input than even having water, okay? So I will create a data frame. So now I will create a feature for water to cement ratio, and it's quite simple. To create a water to cement ratio, I simply need to just divide water by cement, right? So I will say df, then a new feature, which will be, let's say, wc ratio. I will create a new column here, and then it will simply be water, which is this one, water, and then divided by df cement, right? Then I can display my data frame now and see if this has been added. And now you can see that this has been added. So in this case, you see that the water to cement ratio is 0.3, something meaningful. But in here, look at this. This is so high. This is 0.85, a lot, okay? And then, I mean, it is understandable that the strength is this small, even though the age is 90. You can imagine this is 28 days. We have about 80 kilonewton, 80 Newton per millimeter. And this is 90 days. Despite the fact that it is 90 days, we have this low strength. I mean, it is understandable from this water to cement ratio. That's just me judging, okay? So we go to the next step. The next step now will be to check for the correlation. But before you might be wondering now, oh yeah, we've done the correlation. Yeah, we've done the correlation earlier. But now that we have created a new column, we also need to see the correlation of this new column. But then before we do the correlation, I can imagine something. I mean, we are expecting something. We are expecting to see a correlation between water to cement ratio and water, and also to see a correlation between water to cement ratio and cement, because certainly this column was created from those two features. So, right? So to check the correlation, I think probably I just need to copy the correlation. I don't know which will be faster, whether we do it ourselves or just copy the old code. Yeah, maybe we copy this, Ctrl+C, and then I paste it here. I will call this Pearson correlation. This will be df.core Pearson correlation. Then maybe I can hide this for now. Okay, let me just comment this out for now. So if I run this, this is what I have. Let's see the correlation between water to cement ratio and cement. So the correlation between water to cement ratio and cement, you can see it is very, very high. It is 0.88. Although it is a negative correlation, but you can see the strength. It is very, very high, the intensity, okay? So if we do the same thing and check against water, okay, water to cement ratio against water, it is a positive correlation, but it is not as high as it is with cement. So I'm guessing cement will have high collinearity. It will have multicollinearity with water to cement ratio. All right. We can just move forward to the next one. This is about visualizing the correlation. I think we can also copy this. I will simply just maybe copy this. Ctrl+C. And then Ctrl+V. In this case, I don't need to do a subplot because I only require one. I will use plt.figure. Okay, and all of this grid will not be required. Then I will take away all of this. Then data frame equals to this. Axis equals to, well, there's no ax. Okay. Then this will just be plt dot title, not set title anymore. Okay. Then we can run this, and this is what we have. All right. So I don't expect to see much different except for the water to cement ratio that we have seen ahead. Okay, which is, high with cement, and then with water. Where is it? Yeah, and this is it for water. So it has very low with super plasticizer, and then the correlation with the, let's see what's the correlation with the strength itself. So it has a correlation of minus 0.49. So let's see what is the correlation of cement alone with strength. Cement alone with strength. This is cement. Okay. So cement with strength is 0.47, which is this one. And then water to cement ratio with strength is minus 0.49. So there is a little bit, just a little bit 0.02 difference. So possibly when we use water to cement ratio, we are able to get a little bit linear relationship, just 0.02 more linear relationship with strength than using cement alone. Okay. So I think that makes sense. Okay. Then for the mutual information, we can simply copy these as well. I would say, let me Ctrl+C here, maybe Ctrl+V here. Then I copy all of this, Ctrl+C. Okay, I'm just trying to make it fast since we've done it before. It will not. It doesn't make any more. So MI score equals to mutual information. Okay. So in here, yeah, I think it will still be the same. I run this. No, it's not the same actually. So MI score equals to X. Let's quickly just split our data so that this understands what X is. So X equals to df.drop and then columns equals to strength, and then y equals to df, and then strength. Okay, so now if you run this, we will have the new feature, which is water to cement ratio. And you would see that initially the one that has the highest information was age. Cement itself comes third, water comes second. But now that we've been able to combine water and cement as a separate entity, we now have more information that even comes before age, because initially age was leading. But now water to cement ratio is leading. Okay, so in my opinion, I think this is a very good feature engineering. This feature that we created has more information than cement alone, and it has more information than water alone. So when we combine these two together by simply having that ratio, we are able to get more information and reduce the uncertainty in predicting the strength of concrete. All right, so we move to the next one, which is to check the multicollinearity. As you would expect, there will be multicollinearity between the water to cement ratio, water and cement. But let's see. I will copy the code again. I think this is where we did the multicollinearity stuff. So I will Ctrl+C, and then I will Ctrl+V. Then I will simply just run this. VIF equals to, okay, there was one line above, which is this one. Okay, so I will simply just copy this one. Now, if I run, it should have the full details. So now we have the water to cement ratio. So that makes sense. Now, if I check the results, as I said, when we have if we have a VIF between 0 and 5, we can regard that as good. We say this is fine. If we have something between 5 and 10, we consider that as moderate. It is not entirely good, but at least it is moderate. But when we have a VIF greater than 10, then it is not good enough. Now, if you check for cement now, you will see that the calculated VIF for cement is high. All right, it is very high. It is 12. So that tells us that cement has to go, okay? Because this is greater than 10. This is greater than 10. So, and we understand why this is 12, because initially what we had was 7.4, but because we have created a different feature from this cement, it is now having some information about this new feature, and that is the concept of multicollinearity itself. Okay, so now that we see this, we have to kind of drop it. So it's either we use cement and water, or we simply just use water to cement ratio. And as we have verified from the mutual information, water to cement ratio alone carries more strength. It carries more information than using water and cement. So in my opinion, we can drop this and just use water to cement ratio. Okay, so that will take us to the last step, which will just be to select what the feature is and select what the target is. So from our analysis, we will just drop cement, I would say. So I would say now my x equals to df.drop. Okay, then the columns, well, initially we've been dropping just the strength, but in this case we're not dropping the strength alone. We will drop cement, and we will also drop strength, because strength is the target, so it cannot be that. So, and then for the target, of course, the target will simply just be the strength, right? So if you do x.head to see your the feature, you'll see this is what we have. 1, 2, 3, 4, 5, 6, 7, 8. It is still 8, only that we don't have cement. What we have is water to cement ratio. And if you do y.head, well, we don't expect to see anything different from what we've been seeing. So this is what we have. So this takes us to the end of the data engineering concept. And then in the next episode, we will just go into the fourth phase, which will be about classical machine learning. Then we will do linear regression, we will do ridge regression, we will do lasso, we will do polynomial regression. And then we'll also see some other machine learning models. So see you in the next episode.